Okay, so this talk is a technical deep dive into how we actually implemented the feature of adding lambdas to Java. So this is not a sort of language overview. This is much more of a exploration of what were our implementation choices, what choices did we evaluate and reject, what choices did we ultimately take, to give you a sense of how these things are actually built. So in some sense this talk is mostly useless because as programmers we're just going to use these features where very few of us are actually going to implement them. But I always like to know how things work, and I think a lot of us do. So this is mostly to give you a sense of what's going on at the layers, 1 and 2 layers below the code that you're writing. Okay, so I work for Oracle, so I'm obligated to show you this legal disclaimer slide, and moving on. Okay, so highly technical talk. Hopefully some of you have some familiarity with JVM and Java bytecode. How many people here have used the Java P tool to dump out bytecode? Okay, about a third maybe. Okay. So if you haven't, and you have a laptop right now, you might want to try it. So Java P is a bytecode dumper. So the Java C compiler takes Java source code in, writes Java class files out. The Java class files use a architecture-neutral intermediate representation called Java bytecode, which then the VM translates to native code at runtime. So if you want to know what bytecode, given source constructs, correspond to, or what's in a Java class file, Java P is a good tool for learning that. I'm going to show you some bytecode. I'm also going to talk about some of the facilities that were added in Java 7, specifically method handles and invokedynamic, which again, not something that anybody who is not implementing languages is going to use, but again, good to know about, just to understand what's going on. All right, so I'm going to do a ultra quick overview of the features that we added to Java 7, just so you can see what the source code looks like. I'm assuming everybody in this room has a pretty good idea of what a Lambda expression is from their favorite language, so I don't have to belabor this. Lambda expression in the context of Java is an anonymous method. It has everything a method has. It has an argument list, it has a body, it has a return type, it has a set of thrown exceptions, but we've compressed away most of the syntactic boilerplate to get it into something a lot smaller. So here's some examples of Lambda expressions. In the first one, we have an argument, takes one argument, it's a person. The body takes that person, gets their name, adds them to some list of names. The manifest type on the argument can be left out if the compiler is able to infer it. So in the context of a statement like people.forEach, and you're passing in something that takes a person and returns void, the compiler is able to say, oh, well, I know E is a person because what else could it be? And if the compiler can't infer it for you, you'll get a compile time error message. So it might look a little bit like dynamic typing. It's actually the same static typing Java has always had, just with less boilerplate. Lambda expressions can capture values from the enclosing context. So in this last expression, min age is defined outside of the lambda, and so that's considered a captured value. Okay, not all lambdas are capturing, but capturing fits largely in the translation scheme. So I'll have a couple of examples of that. So a little bit of background of why it is that we're doing this in the first place. Why bother adding lambdas to Java? I talked a little bit about that in my talk this morning. Couple of major reasons. The most important of which is providing a path to building multi-core friendly libraries. So if you want to build parallel friendly libraries, you have to have a way of expressing code as data, so that you can say, here, do this for every element of the collection, and you work out the details of the parallelism, decomposition, etc. A lot of other reasons. We want to empower library developers to write better libraries. We want to keep up or catch up with the competition. And we've had a tool for this in the form of inner classes for a long time, but it's just too clunky and not suitable. So what we're going to focus on in this talk is the question of runtime representation, how we represent Lambda expressions at runtime, what it looks like in the bytecode, what it looks like during execution. And as much as runtime representation is an implementation detail, it also is important. On the one hand, yes, we should design the language to stand on its own, but you want it to run efficiently on the JVM as well. And if there's a mismatch between how things are represented at the language level and how they're represented at the VM level, this is going to be ongoing pain for your users. So we want to keep the language view of the world and the runtime view of the world as aligned as practical, and that's something that pays dividends. Okay, so the big question number one when you're adding a new kind of expression to a language is, if you've got a statically typed language like Java, what's its type? So what's the type of a language, of a Lambda expression? Most languages that have Lambdas have a notion of function type, function from int to long. So early proposals for adding Lambdas to Java said, well, let's just add function types to Java. And this seems like an obvious idea, but when you start digging, you end up with a lot of nasty questions surrounding representation. So what's it going to look like in the bytecode? What's it going to look like in a method signature in the bytecode? So Java is dynamically linked. When you invoke a method, it selects among the overloads and actually takes the signature of that method, the method called foo that has arguments int and long, and sticks that in the class file. So if we're going to, so we have to find a way to represent a Lambda in a VM type signature. Similarly, how do we invoke a Lambda? Do we have to have special bytecode, for invoking it? How do we create instances of them? Do we do that with a new bytecode or with a new bytecode? It's bytecode called new. That's the old way. Do we have to invent a new way to new? I didn't think this out very carefully. Okay, moving on. The Java language type system has variants. The runtime type system doesn't. Is that going to intrude in the runtime representation? So all of these questions come up when, once you get past the, oh, we'll just add function types to Java. So as most of you, some of you have probably heard, I like this trick of taking an unreasonable question and making it sound reasonable by saying, why not just in front of it? So, people asked, well, why not just add function types? Well, because it's harder than it looks. The JVM has no native representation of a function type, so we would have to invent one, or we'd have to teach the JVM about something new. The closest tool that we have that could represent function types, function from T to U fairly easily, is generics. But that would bring with it a lot of the pain of generics, like boxing and erasure. And boxed function types or erased function types would really stink. So for example, if we had a generic type function from T to U, you wouldn't be able to overload two methods that took functions, even if their types were completely different. So you might write an overload of function from string to int and function from long to double, and then the compiler would say, you can't do that, these have the same erasure. And you'll say, what? Doesn't look at all like the same erasure. So we thought that would be a mean thing to do to people, and we didn't want to do that. And so this is one of those places where there would be a gap between the language representation and the VM representation, and that's always a pain point. So we could teach the VM about real function types, but this would be a huge effort. It would affect signatures, it would affect bytecodes, it would affect verification rules. So this, would be a pretty big deal. So we kind of cast around looking for alternatives because this was a lot of work and we're lazy. So historically, in Java code, we've modeled functions using one-method interfaces, things like runnable or comparator. And we thought, well, all right, rather than add a new kind of type to the type system, how about we just formalize this notion of a function is represented by a one-method interface. So we took this pattern and gave it a name, functional interface, and boom, we're done. That's our function type. So the way the language works is a functional interface like predicate here is isomorphic to a function that takes a t, returns a Boolean. So the compiler looks at predicate and says, all right, that's an interface, but it also could be a function. If it were a function, it would be from T to Boolean. And then when you see a method like, remove if, whose argument is a predicate of T, and someone provides a Lambda expression as the argument to that method, it says, all right, well, I'm willing to convert this Lambda expression to one of these nominal functions. Let's see if the shapes match up. Do they have the same number of arguments? Are their argument types compatible? Are their return types compatible? Are their exceptions compatible? And if they are, then the compiler says, okay, I'm going to take this Lambda expression that takes a person and returns a Boolean, and I'm going to convert that to a predicate of person. Done. And now, if we do this, the signatures look like Java signatures that we've always had. They have these nominal types in them. Invocation looks like the invocation we've always had. So that seems like kind of a simpler way to do it. So sort of there's a lot more detail to this story than I'm expressing on 2 slides. But the takeaway point is just add function types was obvious and wrong. It would have been complex. It would have introduced corner cases. It would have exposed users to more of the pain of erasure, which isn't nice. It also would have had the effect of completely bifurcating the world of Java libraries, because now we'd have old libraries and new libraries. And do you remember the pain we went through when we had generic libraries and non-generic libraries, even though they were interoperable? Right? And there was this 5-year period where there was all this churn about generifying libraries. Well, we don't want to do that again. And so we don't want to create this split between old and new libraries. So by using an old mechanism, we avoid that problem. And as a bonus, existing libraries that were designed years before Lambda, all of a sudden compatible with Lambda as long as they're using this pattern that a lot of libraries already use. So fewer new concepts, maintains investment in existing libraries. Sometimes a stodgy old approach is better than a shiny new one. Okay, so let's look at another question that we sort of grappled with as we designed this feature. How does a Lambda instance get created? What is this runtime representation? So like I had in this example here, we have a Lambda expression on the right, is a function from person to Boolean. We have on the left-hand side, we're assigning it to a predicate of person, which is morally a function from person to Boolean. So the compiler sees this code, it needs to produce some bytecode. So what bytecode should it produce? So there's another obvious solution here. Just spin an inner class. Right? Inner classes have done this for a while. We could just say a Lambda is an inner class instance, and the compiler would generate an inner class like this one, which, since it captures a variable, it has to have a field, it has to have a constructor that initializes that field, and then the body does the obvious thing. Totally simple compiler, operation. We could have been done in a week. A lot of people thought we should be done in a week. But the nice thing about this is Lambda capture translates very straightforwardly into invoking the constructor of this inner class. So the compiler generates this inner class. It generates, for the instantiation of Lambda, just an invocation to the foo$1 constructor, and we're done. And then invoking the constructor translates to some very straightforward bytecode. So what are we doing here? We instantiate an object of class foo$1. We push the captured variable on the stack. We invoke the constructor, and then with the reference to that new thing still on the stack, we just pass that directly to remove if. So very simple, very unobtrusive into the way the compiler generates bytecode today. Okay. Obviously, I've got the scare quotes around just why didn't we do it this way? Well, inner classes suck. And translating to inner classes behind the scenes inherits a lot of their problems, with the added bonus that you didn't even ask for an inner class. So now you have the pain of inner classes without having asked for one. And that's kind of lousy. So what are some of the problems of inner classes? Well, performance. So you're generating a class per Lambda expression. You have an awful lot of implementations of types like runnable, which means you get megamorphic call sites. That's a performance problem at runtime. And you're always allocating a new instance, even when instances are logically equivalent. So even if a Lambda captures nothing, an inner class would still instantiate a new instance. And like sometimes we sort of do this by hand in our code, right? If you have a comparator that's not capturing anything, you like move it to the top of your class. You say, private static final comparator C equals, and you do it once, and then you just pass that. But that's kind of like mangling up your code for performance reasons. We'd like to not put people in that situation. And also the rules about naming lookup in inner classes is really nasty, and we wanted to avoid exposing people to that. So the important thing to recognize is whatever bytecode the compiler generates on the first day that Java has lambdas is the binary representation for lambdas until the heat death of the universe. So we want to pick that representation very carefully, and ideally that binary representation with the implementation choice we happen to have made when we were writing the compiler, because that constrains us pretty terribly. So I think this is another one of those obvious but wrong choices. So let's look at some other options. In Java 7, we added a feature called method handles to the VM. Now, this is a low-level feature that's designed, it's really a toolkit for compiler writers. But the idea is it's like reflection, but it's actually fast. So you can store a reference to a method in a method handle. You can put those method handles in the constant pool and load them as constants, and the VM makes that really fast. You can obtain a method handle for any method or any constructor or any field accessor. And the VM understands method handles, so it happily inlines through them. And it provides you an API for manipulating method handles, like adding arguments and removing arguments and adapting arguments with boxing or unboxing or casting or what have you. So basically it's a compiler writer's Swiss Army knife. So this seems like another one of those obvious choices. Lambdas are a language level method constant. Method handle is a VM level method constant. How could this not work? So we could use method handles as our implementation technique. That would involve, we would have to desugar the body of a Lambda expression into a method. That's easy to do. And then represent the Lambdas using method handles in bytecode signatures. And that's where things start to fall apart. OK, so here's how the compiler would translate things if we have the exact same code as before. So we would say, take the body of this Lambda, desugar it into a method. Here we've called it lambda $1. We give it an extra argument, which is the captured min age. That's coming in from the outside context. And of course, the argument to the Lambda expression, the person, and the body just evaluates it. And then when we go to generate code for the capture and the invocation, all we do is say, well, give me a method handle for the desugared method. And then stash this extra argument on it, min age, and then just pass that to remove if. So the signature of remove if would be remove if method handle. Well, that's kind of a problem because method handles are effectively erased, right? There's just one method handle type. There's not method handle for function from int to long. There's method handle. So this is like super erasure. So if erasure sucks, this is even worse. We wouldn't be able to overload two methods that take even differently shaped lambdas or different arity lambdas. And we'd still would need to encode the language level type information in the class file somewhere, even if it's not encoded in the bytecode. So this suffers from the same problem as the last obvious but wrong choice because it takes an implementation technique and it conflates our binary representation with that choice of implementation technique. So again, nice idea, but doesn't quite do what we want. So I know this is only taken like 20 minutes so far. We've just described a period of like 6 months of beating our heads against various options. OK, so what have we learned here? What we'd like is a binary representation that is not tied to the specific implementation. Certainly, we don't want to carry with us the baggage of interclasses, and we also don't want to carry with us the low-levelness and erasure of method handles, and we don't want to pick something that we're going to want to change because we don't want to ever say to our users, oh yeah, there's a new version of Java out there and it's much faster, but yeah, you got to recompile all your code. We don't do that. We don't want to do that. Users wouldn't like that. So we took that as a requirement. We can't ask users to recompile just to get more the additional performance that we might have in a future version of the JDK. So, of course, the solution to all problems in computer science is more indirection. And the challenge is, how do we make it so that additional indirection doesn't hurt us performance-wise? So the theory is the compiler could emit not code to construct the Lambda, but something more like a declarative recipe for how to make this Lambda. And the runtime would execute that recipe using whatever tools it decided at the time was best, whether maybe on Tuesdays it would be interclasses and on Thursdays it would be method handles, but we don't care because that's now a pure implementation detail as long as it's fast. It has to be fast. For this, we turned to another VM feature that was added in Java 7, again, not a feature for users, but a feature for compiler writers, called invokedynamic. So let me talk a little bit about invokedynamic. Prior to Java 7, there were 4 invocation modes, 4 different bytecodes for invoking methods. They were invoke static, invoke interface, invoke virtual, and invoke special. And they correspond pretty straightforwardly to Java language situations. One is for static methods, one is for interface methods, one is for virtual methods, and then one is for everything else. So invoke special handles, constructor calls and super calls and private methods and all the things that don't fit neatly into one of the other 3 buckets. And we saw examples of 2 of these in the bytecode representation for the inner class. We used invoke special to invoke the constructor of foo$1, and then we used invoke interface to invoke the removeIf method. So Java 7 added a new one, invokedynamic. We abbreviate this to Indy. It's different from the other invocation modes. The other invocation modes have very fixed and Java-like invocation semantics, but we recognize that not all languages are like Java, and not all languages want JVM invocation to work the way invocation works in Java. And so the basic idea behind invokedynamic is it lets the language runtime and the VM be partners in linkage decisions, but also provides, so it provides a way for a language-specific logic to help the VM resolve a method call, and then get out of the way so you don't have to be calling into the language runtime on. That's how we make it fast. So, you could have, JRuby code that provides JRuby-specific linkage logic. Jython code provides, Python-specific linkage logic. And ultimately, that boils down to one of the old invocation modes that the VM already knows how to inline through once the resolution is done. So this started out as a tool for dynamic languages, where the language didn't have all the type information available that Java JVM signatures need in order to be able to do a method invocation. So as an example, like here's some code in Ruby where you say, I have an add method, takes 2 arguments A and B, and its body is A plus B. But since we don't know the types of A and B, we don't know what that plus really means. That could be 2 integers, could be 2 floats, could be 2 strings. So we don't know the types of A and B at compile time. We know them at runtime. The types could change from call to call, but the reality is they usually don't. If I call this method and then I call it again, there's a really good chance that I'm going to have the same types in my arguments as I did the last time, because we call things in loops, right? So you have some loop that's iterating through an array, and you're calling this method, multiple times. I want to be able to reuse linkage decisions without having to go through the slow path of what's the type of A, what's the type of B. Let me look up in my function table the plus method that corresponds to these 2 types. You could obviously do this with a reflection, but it's really slow. And so, the key here is we want to avoid relinking the call site by embedding information about when it consults the language-specific linkage logic, it says, here's the thing to call, and here are the conditions under which you can just reuse this decision without having to come back and recompute the linkage target. And once the VM does that, it's then able to inline through the, the invoke dynamic call just like anything else. Is there are multiple phases for a given invoke dynamic call site. The first time you invoke a given call site, it has to do some expensive one-time linkage work. So it consults this language logic, which we call the bootstrap method. And that's going to do some work. It's going to do some lookups. Maybe it's going to spin some classes. It's going to do whatever it's going to do. But it only gets done once. And then it returns a link call site, which embeds, here's your linkage target, and here are the conditions under which you might have to relink. And thereafter, if those conditions aren't present, the VM never has to consult the bootstrap method again. So afterwards, the VM can treat the call site as being fully linked and then inline it through just like any other call site. So it's a pretty cool tool. It allows you to do some one-time work and then reuse that decision. And this is what we ended up using in our translation of Lambdas, even though Java is a statically typed language. This is theoretically a tool for dynamically typed languages, but why should they have all the fun? So if you look at what's in the bytecode at an invoke dynamic call site, there's basically three groups of operands. The first one is the linkage bootstrap, which contains your language-specific linkage logic. That's called once, never called again. There's also a dynamic argument list, which is pushed on the stack, just like any other invocation instruction. And then there's another argument list, the static argument list, which is constants that come out of the constant pool. And that is the argument list that's passed to the bootstrap method. And it captures things about the call site, such as the types of arguments and things that the compiler knows statically. So, like I said, Java is a statically typed language. All the types involved are static, so we're not using the dynamic relinkage feature of invoke dynamic. But what is dynamic here is our code generation strategy. We outlined two code generation strategies before: spin and enter class, or use a method handle. There are others too. We could use dynamic proxies if we wanted our code to be really slow. Or maybe we're running on some VM that has some really low-level method for building objects out of pure bits and alchemy and such, that we want to use that for making our lambdas instead of the other mechanisms. So we have these various implementation strategies, and that's what's dynamic. We want to dynamically choose between those translation strategies, and invoke dynamic gives us the chance to turn this choice into a pure runtime implementation detail that's completely separate from the binary representation. So that's a really cool trick, and I'll show you more of how that looks. So the concept is, in the bytecode, we embed a recipe for constructing a lambda. So what goes into that recipe? Well, we need to know the body of that lambda. So we're going to do the same thing we did in the method handle translation case, where we desugar the lambda body to a method, and we use a method handle to represent that method. We need to know the target type. What type is this lambda being converted to? In the examples we've shown so far, it's been predicate. So that's one of the things that the bootstrap method needs to know. And then there might be additional metadata about the call site, such as, like, do I have to do special things for serialization? Or what are the variables that are captured from the lexical scope? Because those are going to be needed when constructing the lambda. So this, we represent this using an invoke dynamic call site. We call this the lambda factory. So the idea is you invoke this invoke dynamic call site, and it returns you the lambda that you want. Some of the arguments to the factory are static, and they're encoded in the constant pool. Some that are dynamic, they're pushed on the stack. And then the VM makes it the case that subsequent invocations of the same factory site, in other words, subsequent captures of the same lambda, you bypass the slow linkage path. So, okay, let's look at what the compiler does. So first step is desugar the lambda body to a method like before. So here we have this method, lambda $1. It has the argument, person p. It has the captured argument, min age. So that's easy. Very straightforward transformation. Generally, we can translate this to a static method. If it's a method that captures the receiver because it touches a method or another class member or invokes one of the class methods, then we desugar it to an instance method. And then at the site where we want to capture the Lambda, we emit an invoke dynamic instruction, where we say the bootstrap is this special Java language runtime language logic method called the Lambda metafactory. The static arguments are what is my conversion type, my conversion target, here predicate, and where's my implementation, here lambda $1. And the dynamic arguments are the min age that I've captured from the context. So I invoke this call site, it hands me back the Lambda I want, it's of type predicate, and then I just pass that to remove if. Okay, so the nice thing is, we're using this nominal representation of functions. The signature of remove if is just predicate. The Lambda capture creates a predicate. We just pass that along. Okay, so the generated code is actually pretty straightforward. If you use Java P, you can see all of the invoke dynamic stuff in the constant pool, and we didn't have to distort the translation very much. So that's pretty good. So now we have this, this thing we call the metafactory, the bootstrap method for these Lambda capture sites. It could do anything it wants. It could generate an inner class dynamically, spin the class at runtime using ASM. And then it would just link the call site to the constructor of that generated class. That's actually the initial strategy that we implemented, but that's just the version 1 strategy. In the future, we could do something like, instead of spinning one class per Lambda, we could spin one class per functional interface type, one wrapper class for runnable, one wrapper class for comparator, etc., and just pass a method handle to its constructor. And we'll do that as soon as we're sure that the performance of that is better. And that's something that we don't have to do in a major update of Java. We could do that in 8.0.1 because it's just an implementation detail. We could also use other techniques like dynamic proxies or method handle proxies or VM private APIs or whatever we can do to make this translation as fast as possible. So what using invoke dynamic gave us here is the option to defer the choice of code generation strategy to runtime. And therefore it becomes a pure implementation detail, something that we can change from version to version, from day to day. We settle on our binary protocol now, which is, here is the API for this invoke dynamic bootstrap. But we haven't burned the choice of implementation strategy into the bytecode. So this is a classic Java trick of move more of the work from static compilation time to dynamic runtime when you have more information, right? If you have more information, you can make better decisions. The reason dynamic compilation always blows away static compilation is you have more information at runtime than you do statically. And this gives us the flexibility to change our code generation strategy whenever we come up with a better one. But wait, there's more. This behavior that invoke dynamic has, where the first time through you link the call site, and then future times through it bypasses that, gives us basically for free that trick I was just describing, where you take an inner class and you stash it in a static field, public static final comparator C equals, new blah blah blah. That trick that we used to do by hand to reduce the number of allocations in our code, now the runtime just does for you for free. So if you have a Lambda that doesn't capture anything, and a lot of Lambdas are like that, x arrow, x plus 2, or something like that, the compiler is going to say, this is a stateless Lambda. One instance is as good as another. They have no identity-specific characteristics. So the first time I capture one, I'm going to stash it at the call site, and then thereafter, I'm just going to return that same one. And the VM is going to recognize this pattern and turn Lambda capture into a constant load. So this makes, in the fairly common case of stateless Lambdas, Lambda capture much, much faster than inner classes because you're not allocating, you're not going to the heap, etc. So in this case, you can think of invoke dynamic as being a lazily initialized cache. It delays initialization to the first use, so the overhead is 0 if it's never used. You don't need an extra field, and then all stateless Lambdas get the benefit of this lazy initialization and caching that comes for free. So remember I said we need another level of indirection, but we don't want to pay for it. So let's look at the performance cost here. What we're calling the Lambda metafactory is only invoked once per Lambda. In the case of non-capturing Lambdas, which is pretty common, subsequent captures are free. I mean, totally free. And for the capturing case, subsequent capture cost is on the order of a constructor call, which is basically the same as inner class. So we have a performance characteristic, which is worst case, just like inner classes, best case, better. So that's pretty good. So let's break this down a little bit. If we look at the different layers of cost involved in translation from Lambda to bytecode, there's really three significant layers of cost. There's linkage cost, which is the one-time cost the first time you capture that. So in the case of inner classes, linkage cost looks like class loading, right? The first time you instantiate a given inner class type, which translates down to like new foo $1, it's got to go to the file system, read those bytes off disk, load the class. The next time you capture that same kind of inner class, you don't have to go back to the file system and read those bytes off disk because you've already loaded the class. So that's linkage cost. Capture cost is what you're doing each time you're capturing an instance. So in the case of inner classes, capture cost is invoking the constructor. And then you have an invocation cost, which is every time I actually invoke the Lambda or the inner class method. And that's just an ordinary old invoke interface bytecode. Okay, so we have these three layers of cost: the one-time cost, the per Lambda cost, and the per invocation cost. For inner classes, this corresponds to class loading, constructor invocation, method invocation. So let's stack up Lambdas against that. So we got some measurements from our performance team. Here, this is showing us linkage cost. So this measures total time in milliseconds for capturing 32,000 distinct inner classes or Lambdas. We've also, to avoid biasing the results, we loaded all the inner classes onto a RAM disks to take away the cost of actually going to the disk and pulling those bytes in to make it a fairer comparison. And there's sort of four experiments here. One is for capturing, one is for non-capturing, and the other axis is whether we're using tiered compilation or non-tiered compilation, which turns out to have a big difference on the performance. And what we see, the important thing is this last column, which is the percentage difference between Lambda and anonymous class. And in all the cases, Lambda capture is faster than inner class capture. For the, linking a Lambda involves invoking the bootstrap. It's going to generate some bytecode on the fly. You're going to load that class on the fly. Sounds like a lot of work, but it's still less work than an inner class. Okay, so on the linkage side, faster startup. So that's pretty good. All right, so let's look at the capture cost. All right, so these numbers are a little bit different. These are ops per microsecond. So instead of total time, it's throughput. And we measured 6 scenarios. On the x-axis, we have the inner class, the non-capturing Lambda, and the capturing Lambda. And then we have 2 columns here. One is for 1 thread. One is for 80 threads on an 80-way server, banging as hard as they can. And what we see is, not surprisingly, capturing Lambdas are exactly as fast or slow as inner classes, and non-capturing Lambdas are faster in the single-threaded mode. And when we go to the saturated mode, non-capturing Lambdas are way faster than inner classes. Okay, so going from single-threaded to saturated, we see a 5x improvement in throughput for the inner class case and the capturing case, but an almost 70x increase in throughput for the non-capturing Lambda. And that's where that trick of caching the Lambda at the call site and turning it into a constant load really pays off, right? You don't have to do any heap management overhead, which has an impact on scalability. Even when you're allocating with thread local allocation blocks, eventually you have to go back to the heap to get a new thread local allocation block because you've run out of the one you have. And that shows up as a scalability impediment. So pretty good story here. Our worst case numbers for Lambda are exactly the same as in our classes, and our best case numbers are much better. So this is, what game theorists call a dominating strategy. And note that this is just our dumb strategy. This is just the version 1 strategy we're going out with. Simplest, dumbest thing we could possibly do. So there's a deep pipeline of things we can do to make it faster, but even if you don't believe us about that, it's still faster even with the dumb strategy. Okay, so one of the other cool things about this approach that we've taken is the Lambda conversion metafactories are part of the JDK. So even though the semantics of them are tailored to what the Java language needs, other languages might find this useful also, because other languages that run on the JVM may want to invoke methods on collections and may want to convert their lambdas to the representation of lambda that the collections are expecting. So Java APIs are going to be full of these functional interfaces, like collection.forEach or the remove if example we've been using. And so other languages may want to call these APIs, and we'll get the benefit of all of the performance improvements that we add to them over time. Obviously, other languages can do what they want, but it's one more tool in the toolbox for other language compilers to piggyback on the work, the performance work that we're doing for the Java language. So not just for us, anybody can use this. Now, I mentioned there's sort of a deep pipeline of VM optimizations that we really want to do here. So with a little bit of help from the VM, right now, we got no help from the VM. We're just using invokedynamic out of the box. It's just like any other compiler would, like JRuby would. But with a little bit of help, we can do better. So one of the optimizations that we've got in mind is we've designed the API of the Lambda metafactory to have semantics that map perfectly to method handle algebra. So the VM could look at a Lambda capture site and say, oh, I know exactly what that does. It has the exact same semantics as this equivalent method handle combinator. And since the VM already understands method handle semantics, it's an opportunity for the VM to then do things like apply other optimizations like code motion and box-on-box elimination. So for example, like the capture operation is a pure operation, has no side effects. So if the VM can intrinsify the capture operation, it can say, all right, I can freely move that capture operation through an inline call, for example. I can defer actually doing it until I know I'm going to need it. Or if you think of Lambda capture as basically being a box operation, you're taking a method and you're boxing it into one of these nominal function types. Well, the same techniques that let us do box-on-box elimination on integers could apply to functions, where you have this boxing operation, you move it to where the unbox is, which is the invocation, and then just say, oh, well, what do I need the box for? Let me just invoke the method handle directly. So with a little bit of work, intrinsification, we can lean on other existing optimizations such as inlining and code motion and escape analysis to make Lambda capture even faster. So that's pretty cool. Okay, so I have to talk about serialization. I hate serialization. But no language feature is ever complete without some interaction with serialization. So here's why we had to tackle this. We've made this decision to represent lambdas as nominal function types. So if we have a nominal function type called foo, and it extends serializable, and here this is a function from void to Boolean, and we assign a very simple lambda to this, users are going to expect this to work. And if we say this doesn't work, it's just another edge case that users have to reason about of like, oh, this thing is serializable if it came from an inner class or a name class, but not from a lambda, so I have to reason about its provenance, and we don't want to ask people to do that. Unfortunately, because our translation strategy is dynamic, we can't just serialize the lambda object because the class that represents it won't exist at deserialization time. So we have to, and even if it did, maybe it's using a different translation strategy, and we'd like to deserialize it using the translation strategy of the target VM. So we have this dynamic translation strategy. We need a dynamic serialization strategy too, and without introducing any security holes, which is hard to do with serialization. So the trick here is, just like the Lambda capture site is a recipe for a Lambda, the serialized form needs to be a recipe for the Lambda as well. And we can use the existing hooks in serialization, read, resolve, write, replace, to serialize to a recipe of, here are all the things that went into the call site. And then at deserialization time, we reconstitute that into into a new Lambda capture using whatever translation strategy is current at the time. So it all does work. It's pretty nasty. Hopefully you won't notice it. It'll just work. But I'd like those months of my life back. Okay, so summing up. The evolutionary path for evolving a language is full of ideas that are obvious but wrong. And you really have to be on the lookout for these obvious but wrong ideas, because they're so compelling. It's like, oh, I have the perfect tool, except it's not perfect. And boy, it's not perfect in this way either. And so you have to be willing to keep looking. And some of these approaches that I described took a number of aha moments to get from the obvious but wrong, but to the actually right. And when we hit the right ones, it was really obvious they were right. But it took us a long time, to find them. And so you have to be willing to keep looking, even though you think you found something obvious. So invokedynamic turned out to be a great tool here. So we use it to capture lambdas. It gave us flexibility and it gives us performance, and it gives us the opportunity to change our strategy at runtime. And even using the dumb strategy that we're starting with, still at least as good, and possibly better than inner classes in common cases. So hopefully, like I said, none of you will ever have to know any of this. You'll just use lambdas and you'll get great performance and you'll be happy. But, if next time someone says, oh, lambdas are just syntactic sugar for inner classes, now you can slap them around authoritatively. If you're interested in more information, you can go to the Lambda project page on OpenJDK. You can download the spec, you can download the binary, you can download the overview documents and play with this today, or wait till Java 8 comes out first quarter next year. And with that, do we have any questions on the magic question machine? All right, so first question here is, how did Java Lambda performance compare to Lambda performance of other languages? So I don't have data for this, but I am sure that we're going to blow them all away, because all of the others are using the same tools that we rejected as being too slow. Okay, and now of course they're welcome to use the tools that we have, and I expect some compilers will migrate to using them, but have a hard time imagining that they're going to do much better. But I'm always willing to be proven wrong. Okay. Let's see. I'm not going to answer that. What feature in regards to Lambda which didn't make it in is your biggest regret? That's a good one. Do I even have an answer for that? So many little things didn't make it in that things that would be little rough edges, but I actually can't think of anything big that we really regret leaving out. Maybe that's just me convincing myself of something. All right, you have some other questions on the mic, George?
So you now told us about lambdas, and this morning you also talked about value types. So I just wanted to know if you're going to give us tail calls as well at some point.
So tail calls. So that's a good question, and a common question, one that we've received at every conference for the last 15 years. So what was that? Now actually is the time, and the reason for that is, the reason we haven't been able to do tail calls, despite the fact that it is so obvious how to do tail calls, has been a subtle one, and that is there's an interaction between how one might implement tail calls in the JVM and the security model of the JDK. So there is code in the JDK that, for whatever reason, I'm the messenger, don't shoot me, relies on how many stack frames are there between me and the last code domain. Okay, so if you have the language runtime systematically munging the stack, you can't rely on being able to walk down the stack and count the number of stack frames. And there was code, security-sensitive code, that depended on, I know that 4 frames down from me is the user code, so I'm going to execute with the user permissions of that code. This is, of course, brittle and difficult, but what it meant was we couldn't have tail calls messing up the stack depth. So that was totally non-obvious, accidental reason why implementing tail calls on the JVM was just harder than it looked. Fortunately, we've just gone through a huge effort to rip out all of the stack depth sensitive code from the JDK and replace it with a more general mechanism about caller sensitive code, where it walks down the stack and looks for the next protection domain as opposed to the specific number of stack frames, which I think has removed the last really serious impediment to moving forward with tail calls. So we are much closer now than we were 2 or 3 years ago, but I'm not going to make any promises about when it's going to be. Okay, if you decide to change the strategy for generating lambdas, which components need to change? The compiler, the libraries, the VM. Only the VM, actually not even the VM. The only thing it needs to change is a little bit of code in the JDK runtime. And this is the implementation of the Lambda Meta Factory. This is something that we can freely change from version to version, even in maintenance releases. It's all pure Java code that changes. It's just an implementation detail. So no language change, no compiler change, no VM change, no library API change, just library implementation change. So that's pretty cool.
I was just wondering, you talked about default methods this morning, but if you have a default method in 2 interfaces, doesn't that give you the same multiple inheritance problem that?
Okay. So the question is, oh my God, you added multiple inheritance to Java. Multiple inheritance is really complicated, right? That's your question? Yeah. Okay. Java has always, here's my clever answer. Java has always had multiple inheritance of types. Class A implements I, J, K. That's multiple inheritance. What we added in default methods was multiple inheritance of behavior. Where all the pain of multiple inheritance comes from in C++ is multiple inheritance of state. We don't have multiple inheritance of state. So the rules for resolving conflicts in default methods are actually really simple. There's 3 rules. First rule, superclass wins. In other words, if the superclass chain has an opinion on that method, you're done. Don't even look at the interfaces. Looks just like it did in Java 7. Rule 2, subclasses win over superclasses. So if list and collection both offer you an implementation of some default, you take the more specific one. Rule 3, no rule 3. If you don't get a unique answer from rules 1 and 2, you implement it yourself as if it was abstract. Very, very simple. Diamonds are no problem. You can have diamonds. They work perfectly. So all of the things that we're scared of about multiple inheritance from C++ are, they all have to do with multiple inheritance of state, and we don't have that problem.
Does that break backwards compatibility?
No, it does not break backwards compatibility because if you're looking at compatibility for, with pre-Java 8 code, if it linked under Java 7, that means that there's an implementation in the superclass chain. Rule 1, which gives priority to the superclass chain, means it works exactly in Java 8 the way it worked in Java 7. It's way simpler than it looks, I promise you.
Okay, thank you everyone for attending. Thank you, Brian, and have a good break.